All right. Over the next week or so, we're going to learn how to build DC circuits and think about um, how those circuits work. Um, in order to do that, we need to know what an electrical circuit is and what current is. So we're going to start there with this little video. When we talk about circuits, really, we're talking about current. Okay. So what is current? Let's define current. Current is the movement of charge, Q, per unit time. So here we have a wire, and if we had create an imaginary cross section of the wire, we're going to ask, well, how many Qs, how many charges, electrons in this case, are moving past uh, our cross section, right, per unit time. That's what current is. The more charges I move past a given point in a given amount of time, the larger current I have. Why are these charges moving? Well, we know the answer to that, right? That's our electrical field. If an object is accelerating, there must be a force. And if a charge is accelerating or moving, there must be some kind of electrical field there. Where do we get a field that can move charges? We can talk about a battery, or we can talk about a plug outlet or a generator. All of these are doing similar things. And what they're doing is you create a voltage difference because work has been done on charges to move the charges toward the like charged terminal. Okay. Conventionally, we talk about moving charges to the positive terminal, right? So if this is a 12-volt terminal here and a grounded 0-volt terminal, we sort of imagine that the charges have been pushed to this positive, and then this positive terminal, and then they want to repel each other. They want to be repelled from this positively charged place, and so they move through the wire. Actually, what's happening is you're moving electrons to the negatively charged space, but um, we don't need to worry too much about that. When we talk about this conventionally, we always talk about current moving from a positive to a negative terminal. So when there's no wire connected there, we have a field, right, between this terminal and that terminal, but it's weak, and there's no way for anything to move between those two places. So we connect it with a wire, with a conductor, or any conductor, and you're going to get a movement of charges from one terminal to the other. So we're going to start with our water metaphor here. So what's happening with a battery? We're moving a bunch of water to a higher place on our mountain, right? We're putting it in the water tower, and that creates a lot of potential energy. Nothing happens with that if we don't have a pipe connection, right? If we don't connect something from the water tower to our house, there's no current. But if we put a pipe in there and open a gate in that pipe, you're going to get a flow of water. In the same way, we have a mass of charges here, and as soon as we open the gateway, we're going to get a movement of charges from one terminal to the other. The voltage difference between your 12 volt and your 0 volt is called the electromotive force. Why? Because motive means movement, right? So it's the thing that moves your electrons, the thing that moves your electricity, and we call that the EMF. And there is a difference between EMF and voltage, but for the most part, we're going to be using those two terms interchangeably. Okay, so when only insulators are between the terminals, no charges move. But when we connect it, you get an electrical field that's created within this wire, right? The field exerts a force on the charges within the wire, and that drives our current. And then the current can be used to do useful work, right? So we can have a lamp, or we could turn an engine, or whatever we want to do. And we symbolize that with this squiggly line here. And this can be a resistor or some load. And a load is that work that's being done. A lamp is a load on your circuit, or a dryer, or a dishwasher, or an engine, whatever, is going to create some resistance. So we map this in a circuit diagram. We have our squiggly line as our load or our resistor. All conductors are going to offer some resistance, but the resistance in this wire is really small compared to the resistance of our load. Okay, so most of the time we're going to ignore the resistance here, even though there is some. And there's also some resistance within the battery, which can matter as well. But in our simplest forms, we're going to pretend we have a voltage here, say it's 12 volts here. It's going to be 12 volts all along here. Okay, so there's no loss of voltage as we move through this wire. Physically, that's not exactly true, but it's a pretty good assumption. If I took out this resistor, okay, and I just had a wire here, there would be nothing. That would be like opening a really big pipe from your water tower, right? There would be no resistance to the flow of that water, and that's called a short circuit. So you need some resistance in your circuit, or that electrical field's just going to move a whole bunch of charges very quickly, which can create all kinds of problems. Okay, I mentioned this before. By convention, we say that the current travels from the positive terminal to the negative terminal. In reality, that's the opposite. Okay, we have an electrical field that points in this direction, right? But we know that's the direction that a positive charge would move. Okay, we don't have. Sometimes you might have an ionic, like a fluid conductor that has a positive ion that moves in that direction. But most of the time, we're going to be talking about electrons moving, and so the electrons are actually going to move from in this direction, right? They're going to move towards that positive terminal.